Okay, thank you. So this is the third talk about SRM, which is strict reverse math. Uh, Juan, did you make available the two notes I gave you?
They are on the program website.
Okay, because they're somewhat polished from the actual talks.
Yes.
And okay, so this talk uh, is about R-based real analysis. Now, this is a wilderness in the sense that there is no detailed set of well-established benchmarking formal systems that have been developed for this purpose, like the well-known subsystems of Z2 and the well-known subsystems of piano arithmetic. Generally speaking, formalized real analysis for reverse mathematics purposes has actually been done ongoing via codings back into the language of Z2. And thereby, so you say a continuous real function is a blah blah blah, a real number is a blah blah blah, you just give a code, right? And thereby consider it as part of traditional RM. This is definitely not the right way to go about any kind of SRM based real analysis. We have seen that strict reverse math anchored in, we have seen strict reverse math anchored in two mathematical realms in these two lectures, which have well-studied formal systems, can be sufficiently well-defined to support active investigations. Most succinctly, given a target non-mathematical standard system and given a strictly mathematical language, find a finite set of strictly mathematical theorems in that language that corresponds closely to that target. In other words, in lecture 1 and 2, I was doing something like this, namely, given a target of non-mathematical standard systems, and like RCA naught or ATR naught, and given a strictly mathematical language, uh, you want to find finite set of strictly mathematical theorems in that language so that that corresponds closely to that target being the non-mathematical standard system. That's what we were talking about. And that's a kind of strict reverse math well anchored in a more well anchored kind of reverse math where I'm not in a wilderness like I am today. Also develop strictly mathematical base theories and obtain reversals over them. In the realm of omega based, so the first lecture was about omega based countable mathematics, where we've seen that we can basically import the whole of RM with base theory RCA naught to strict reverse math with base theory ETF. And that's because ETF is so close to SRM. ETF is so close to RCA naught, as discussed in the first lecture. Um, however, in the realm of Z-based finite mathematics in the second lecture, it wasn't so simple. We can't just import finite reverse math based on fragments of PA, but have to introduce finite sets or finite sequences of integers uh, uh, with carefully designed, strictly mathematical base theories. FSTZ and FSQZ were featured in the second lecture. And we have to solve some internalization issues. Okay, so that's just discussing what was in the second lecture, but you don't have to know, of course, any details for this lecture. Okay, so in more summary about SRM, there's a few major relationships between theories that we encounter in SRM and also in reverse math, regular reverse math. T is interpretable in S. S and T are mutually interpretable. T is a regular extension of S. This is a notion I made up here. If and only if T proves S, and there's an interpretation of T into S, which is the identity on the language of S. This is a very commonly occurring thing. T is a faithful extension of S, if and only if there's a faithful interpretation of T into S, which is the identity on language of S. This is really very strong. This is a very strong notion. Now, there's some other common, even stronger notions that are usually done, but I think more in single sorted and not so clear what it means in many sorted. And this whole subject of strict reverse math depends on many sorted logic, actually. All right. 4 is what we strive for most in SRM developments. And we saw 4 throughout lecture 1 in omega-based countable math, and we saw 4 in the weaker 3 in lecture 2. We saw them both in the SRM of Z-based finite math. All right, now we're going to come to this new thing. I call it a wilderness, the realm of real-based analysis. Once again, you know, the real-based, the formalized real-based analysis is mostly considered part of RM via codings. All right, so the major overall goal of this wilderness SRM for real analysis, the major overall goal of I'll be specific. There's a book on real analysis. There are a lot of books. Well, there are several books like this, but this is one specific one. Real Analysis by Royden, published in 1968. This has been a very commonly used book. And through SRM formalization, give a detailed logical analysis of this book. Now, obviously, it's okay to do a detailed logical analysis of part of the book. Okay. But anyways, the goal is to give a detailed logical analysis. And example findings of such a logical analysis would be the following. The SRM of such and such portions of or modifications of the book forms a finite set of logically presented, strictly mathematical theorems, which forms a faithful extension of, or regular extension of, or interpretable in, or mutually interpretable with one of the famous 5 systems, or some other formal system. Okay, so this is an overriding goal. Take this book, and the SRM of it is you find a finite set of logically presented, strictly mathematical theorems from the book, of course, which forms a faithful, maybe I shouldn't even say this. Which forms a faithful extension of, regular extension of, interpretable in or mutually interpretable with one of the standard systems. Okay. Now, you know, you're going to look at this book and it's not written by a logician. You know, and it mixes some general set theory, which you probably don't want to be, such and such portions. You know, it's general set theory introduction, and so forth. You want to talk about this in the real context of the real analysis, probably, and so forth and so on. So this is up to the researcher to actually make sense of this in a clear way, make this whole thing make sense. Now, I suspect that with this book by Royden, I would suspect that the most likely outcome is that the vast preponderance of this book is going to be at the level of precisely ACA naught, would be my guess. That modifications of the book may be needed to reduce it from ACA naught down. RCA note especially. And when you do that, the role of this is unclear, but it probably is important. And that would be my suspicion, with some excursions that might be higher. But my general feeling is that this is a very basic place. Now, that's sort of in concert with some work of Takayuti. He wrote something in 78, published in 2015 by Princeton University Press, called Two Applications of Logic and Math. And here's the quote from Princeton University Press. In part two, he develops classical analysis, including complex analysis in Peano's arithmetic. Well, of course, you know, with a strict reverse math idea, this is completely absurd, because the language of Peano arithmetic does not capture the language, does not include the language of real numbers, you see. So, you know, this is before, this is, you know, this is some time ago. And so showing that any arithmetic theorem proved in analytic number theory is a theorem in Peano's arithmetic. In so doing, the author applies against its elimination. All right. Anyways, the point is that this is probably worth noting, maybe even taking a good look at. But I think we have to be more, we have to do these things more, do this more along the lines of these lectures. All right, so that's the ultimate goal now, or a major goal of this SRM for real-based analysis. Now, I say real-based real analysis because, you know, there's abstract metrics, there are abstract metric spaces, there's all kinds of stuff that you can't say is real-based, and those create extra issues. What is a metric space? You know, what is the set of points to be allowed, and all this kind of stuff. And it's important to separate that, because you don't want to make this too difficult by bringing in more than one, too many issues. I mean, I did that also. You know, there's a thing called the SRM of countable mathematics, which is much more general, much more difficult probably to organize. So I said omega-based countable mathematics. That was the name in the first lecture. And that's really what's going on in RM, mostly in RM. And then finite-based, Z-based finite mathematics for the second lecture. I wasn't talking about general finite mathematics, which might involve finite sets of real numbers and stuff like that. So I like this idea of, omega-based or Z-based, and then today R-based. So the rest of this talk is to give some illustration as to how such an SRM development might begin to take shape. Now, I have not actually seriously engaged in such a project that I'm suggesting with a real analysis text. Notice the two reals are next to each other, with a real analysis text like Royden. So I'm wandering in the wilderness. So I just want to give you an idea of how you may go about just getting this going. And you may want to get it going maybe even more carefully with looking at exactly what's in this book. Operating in the blind, I start with a motivating one-sorted structure. The domain is the reals. This is the intended interpretation. These intended interpretations I give here are meant to describe the language. But they obviously have an intended interpretation. Everybody knows informally or semi-formally what this means. The reals, the non-negative integers, uh, the integers, both positive, negative, the rational 0, 1, minus, plus, and times. So these are names with minus being unary. And thus I've made a decision here. I'm viewing these to be predicates on this is one sorted. Now there's a many sorted version of this, but I found that you find that if you definitely want to use many sorts, but if you use too many sorts, since we're trying to be formal, the language gets unimaginably complicated because of all the things you have to introduce. So there's a happy medium here that I think is important. And in this case, there isn't much to lose by having these as predicates. And it's simpler to do this. So there are standard axioms for this structure. Namely, we're talking about the ordered field and rings, the ordered ring and then field structure here. And there are obvious axioms for this, which include that every element of Z is isolated, which is, of course, an important point. So I think there's an interesting completeness theorem here. So this is a digression which suggests some more logic projects, which are not really, I mean, they turn out to be important for SRM, but they aren't the main point of SRM. But I think they're pretty interesting. So first, there's a wrong completeness theorem. But before I get into this, if I didn't have multiplication, it's well known that there's a beautiful complete axiomization of this, and it's nice and decidable. If I didn't have multiplication, okay? And in fact, if I don't have N, Z, and Q, then I can keep plus and times, and this is real closed field stuff. There's also a wonderful axiomization, and it's decidable, right? But I've got everything here, and it's important to have everything here. And here's the wrong theorem: the set of all true universal sentences is decidable with a nice axiomization. Of course, this is not true. It's not even decidable either because of Hilbert's 10th problem, right? You all know that. Hilbert's 10th problem rears its ugly head. Negative solution to that. However, the set of all simple true universal sentences in this system is very decidable with a nice axiomization, don't you think? Well, I have to tell you what I mean, but that's much more plausible because it's only horrific things that are causing H10 to kick in here, whatever that means. All right, so I was thinking about this, which probably works. Universally quantified propositional combinations of atomic formulas when there is at most one atomic formula without NZQ, and that atomic formula is linear or quadratic. This would, of course, extend and require to have Carl Ludwig Siegel's proof that quadratic Diophantine equations over Z are decidable. And we also have to know it over N and over Q. Nice axiomization, maybe, probably. For just Siegel's, if you just took Siegel's proof, and maybe Siegel or someone else's proof in the rational case, I'm not sure exactly who did what, but that these things are decidable. I don't think that gives you any. It doesn't readily give you any axiomization. And that's kind of an interesting question because I think he's using some powerful number theory, which involves some complex variables and all that, and a lot of machinery to do this. So that's an interesting question. whether that gives any kind of axiomatization. Nice axiomatization, it seems unlikely. The decidability, okay. And now, simple. Well, if you look at the actual axiomatization of this thing that one would normally want, in other words, just from being a decent algebraist, writing down all the obvious things about this, you see that they're very simple. And now it seems extremely plausible that if you operate at the level of simplicity that this common axiomatization has, then there should be no, then it seems almost certain that if you operate that level of simplicity, that you have all the simple ones, or at least all the simple ones are trivially derivable from the ones that you normally write down. All right, so this is a project that can cut through a lot of stuff when you write down somewhat annoyingly complicated lists of actions, but they're still very simple in some contexts that you can prove. You want to prove that you've listed all of them that satisfy certain conditions. That's what you'd like to have. All the ones that are true that satisfy some simple conditions of simplicity. All right. Simple, true, universal. Yeah. Now, in some cases, you can go to simple, true, period, not necessarily universal. Well, the linear part of that structure, as you know, is has a nice axiomatization, which is, in other words, the part without multiplication has a nice axiomatization, which in fact is for all formulas, not just universal ones. All right, moving on, we're going to need finite sequences in this strict reverse math of reals. And we do this by moving to the two-sorted structure with sorts reals and R star. R star is the finite set of finite sequences from R. I always include the empty sequence. Now, to write this, to axiomatize this decently, we definitely want more primitives, or else we're just flying blind, right? Well, here's a standard list of things you would want. The constant symbol for the empty sequence is convenient. Length is very important. The length of a finite sequence, and you need an axiom that all values fall under the unary predicate capital N. Oh, why did I say that? All values fall under universal. I'm talking about R, first of all. All right, let's fix this. This is annoying. But it's not a sword. Okay, so I think I had several versions of this talk, and I think
You turn the natural numbers into real numbers there on item 2.
yeah, I just typed it different. Yeah, I meant to be just talking about reals here.
You want
Oh,
length to be a
all that.
natural number.
Okay, the lengths. I see. You're right. The lengths go from this comma n into R. Yeah. Oh no. Okay, I'm sorry. I jumped to here. You're absolutely right. You're absolutely right. This is right here. N. All values fall under predicate N. Yeah. Okay. It probably was right in the first place. All right. Fine. Injection. Every real number becomes a one tuple. Every real number becomes a one tuple, and there's a mapping for that. And concatenation takes two finite sequences and turns it into a third. How about this? Okay. There we are. Now the application, in other words, if I have something in R star and I have an integer, but that's an integer is in this sort. Then I produce a value, which is a real. This is coordinate extraction, and undefined unless the second argument lies in n plus. Yeah, I guess I count from one. Yeah. Now you might say, "Oh my God, this mapping is not total." And if you're a well-behaved logician, you like your functions, your primitive functions to be everywhere total. But this is not the case in strict reverse math. You want what's called free logic. You should, there's a thing called many sorted free logic, which is vitally important for detailed work in SRM. And it has its own notation. I mean, I didn't give much of a lecture on that, but that's already worth a half lecture or something to talk about what exactly is going on with free logic and the completeness theorem and all that. It's part of what's called sugared predicate calculus. Nobody wants to use raw predicate calculus. You want to put some sugar in it. I think you want to put some sugar in your coffee, for example. So, this is sugared. All right. Anyways, okay, so these symbols come with obvious accents, which I won't spell out here. Most interesting is this one, probably. The length of cat, this is concatenation. The length of cat is the sum of the lengths. Okay. Now we can start getting into this business of what are the true simple statements and so forth. And that starts to get pretty interesting, I think. We won't talk further about that. So we already have a kind of a pretty substantial monster here where I have to make sure that I put the subscripts to tell you what kind of things these symbols are, right? So we have two sorts, are reals and real star, and we have this relation, this unary predicate on that sort, this one on that sort, this one on that sort, and this constant on that sort, this constant on that sort, this unary function from that sort to that sort, and so forth. Length goes from R star and R into R, and injection goes from R to R star. In other words, a real is a one tuple, becomes a one tuple under INJ. Concatenation takes R and puts it and returns R. And application takes R and returns R. Of course, this application thing is mostly undefined. It's only defined when this length is small. All right, and those remarks actually are part of the axioms you want to write down, right? The obvious axioms. Now, it's very important to go beyond this and have a profoundly new sort for partial functions. And there's an issue about what we're talking about here. So the most natural thing is to have, now, sorts with functions is already present in, was already present in lecture 1 with ETF. And part of this sugared predicate calculus is function variables. Okay, but this is a little twist. This is in the literature you'll find function variables logic, in old-fashioned papers and stuff. But partial functions we really want, because total functions are just a special case of partial functions. Partial functions give us more flexibility. Partial functions occur right away, even though you kind of bury in the rug with the reciprocal function on the reals, right? Reciprocal is not defined at 0. And you don't want to do one over zero is zero by convention, and otherwise it's the usual. You don't want to do that kind of thing. In SRM, you don't want to do that kind of thing. All right, so partial functions from R star into R star, we'd like to have a sort for that, but that's allowed and everything, but we don't want to do this because this will ruin the plan of having a faithful extension of RCA naught. You see, you won't be able to, if you think about that, you won't be able to do that. Uh, because in a faithful interpretation, something is provable if and only if its interpretation is provable. As this would require us making false mathematical statements that limit the partial functions from R star into R star. Now, we can later relativize to certain partial functions, and everything is fine. We'll have faithful extensions. But the main point is this. I want to do real analysis in stages. The next stage beyond this pre-real analysis here, this is just sort of setup, is what I call sequential real analysis or sequential real analysis. A name I've given maybe a little later in this, where we limit the partial functions from R star into R star. We're going to limit them to partial functions from here, from Q star into R. Q star being not a new sort, but Q star is a unary predicate on R star, the sort R star. So we're going to look at partial functions from Q star into R. Actually, that's not quite right. I think that I actually do this. I can't remember. I kept changing my mind. Let me just see if I did that or not. Yes. Okay. So back to here. Yeah. Yeah. Partial functions from Q star into R star. And this makes sense in our underlying logic, this sugared predicate calculus. This makes sense if officially, if this is either a sort or it's a predicate, a primitive predicate, then this is considered legal to have a sort like this. And the axioms for it and all that, and completeness theorems, that's all understood as a sugared predicate calculus. So it's natural to add now when we do this, we might as well add new unary predicates, N star, Z star, Q star on sort R star, arriving at the following intended interpretation. See, these things get bigger and bigger, and they're a lot bigger than this if I didn't do certain things to help matters. Okay. I mean, actual mathematics is just endless stuff like this that nobody pays any attention to because it's all trivial, so to speak. One's not trying to be even completely correct at all, right? In regular math when you write it. Okay, so we get all this stuff. Val is important. This is part of the underlying structure, logic. Valuation of a partial function at an argument returns something, right? So there's this thing called val. All right, with the axioms, and I put it in here. Case can be made I shouldn't have put it in here because it's part of the underlying logic, but that becomes a pedantic issue, and we haven't even really spent a lot of time talking about this underlying logic anyway. So it's there. With the axioms that these new unary predicates carve out the elements of R star, all of which these new ones. Where are these new ones? Here. These three. These three here. These three new ones carve out the elements of R star. all of whose coordinates fall under N, Z, Q respectively, using application. Also, to formulate that, also see that this val maps a partial function and an argument into a value. Yeah. For the action, this is for the action. So val is for the action, although this is kind of a creature of the underlying logic, I think. The action of the elements of the new sort, this new sort, the action of it. This is the environment for what we call sequential analysis. Now, in looking at Royden's book, uh, you may feel that this front end that I'm talking about is just what's needed to get going, or you may look at it and want to maybe start from some other perspective. It's not so clear uh, because there's going to be a lot of material, but I think that this is basically kind of required ultimately, no matter what you do. All right, we're finally in a position to lay down the axioms that come to grips with a real analysis. First of all, we need to import ETF. I mean, we really don't have still much power here yet at all. We need, now in ETF, okay, now I don't want to rely too much on the lecture one, but it had initial axioms and composition, and we need that here. Successor axioms are not needed because we have the ordered ring axioms with discrete Z. Sort omega in ETF is identified with this, so with N sub R, with this predicate here. 1, 2, 3 array functions in ETF are identified with elements of this that map respectively these three things into R star. And the F in these partial functions correspond exactly to certain G. Yeah, this is a little bit of a cryptic remark. If I have a partial function whose values are finite sequences from the reals here, then I can take those indices and put them on the argument side, and the values will now be the elements of the values will now be R. The values will now be just R, or elements of R1, if you like. Yes, maybe this is a little bit cryptic. I'd like to say R here, but I haven't officially introduced it. So take this with a little grain of salt, because I'm trying to be formal about this. But the basic idea is you really do need to know that arguments and mathematicians are doing this distinctively without thinking, right? That if an argument is a finite sequence, you could think of if the value is a finite sequence, you can think of the value as just R, just an element, if you put the indices on the left side as part of your argument. Okay, all right. You won't like it better if I was actually completely formally correct about this. It would be bogged down the talk. All right. Now, so a Cauchy sequence, finally we get to this. A Cauchy sequence is a function from N into R such that there exists G from N into positive N, such that for every M and N bigger than R, the absolute value of f of M minus f of N is less than 1 over G of R. That's one of several variants of everybody's Cauchy sequences. Sometimes one just talks about one of definite convergence, like 1 over 2 to the R or something. But this is better, I think, to talk about it this way. And we want the axiom that every Cauchy sequence converges. See, now we're really getting into what is the real numbers, really. It's important. This axiom. But also when you want the axiom that every real number is the limit of a Cauchy sequence of rationals. All right. Now, this is not really quite enough because there are issues about what is the sequence of reals. It's, infinite sequence of reals and stuff like that. So we need a form of 2 and 3 with uniformity. So a G-Cauchy sequence is a sequence of rationals uh, uh, such that G is a nice map. And for all m and n bigger than r, the absolute value is less than 1 over G over r. So I just put the G in here instead of asking for existence. And if you have a function, if you have a sequence of reals, uh, you want to say that there exists uniformly, you can make these Cauchy that converge pointwise here. So there's a G from n squared into Q and an H from n squared into N. Maybe I need this probably. Such that for all n, the cross-section function, because it's a function of 2 variables, is a cross-section Cauchy sequence with limit f of n. And yeah, that goes backwards, that real numbers are good. Are given by Cauchy sequence. Sequences of real numbers are given by uniform sequences of Cauchy sequences, so to speak, uniform indexed Cauchy sequences. And then if you have a sequence, but a two-ary sequence of reals uh, that's uniformly gives you Cauchy, that's kind of Cauchy of 2 dimensions. Then there's a function f from n. So this is an existence. There's a function n from r such that f of n is the limit of gn. So you can define functions by limit if everything's uniform. Now, look, this is more complicated because I'm trying to do a faithful interpretation, a faithful extension of RCA naught, not a faithful extension of ACA naught. RCA naught. This is harder. Just like the whole coding back in RM of real analysis that stays in RCA naught is trickier than the crude coding that's good enough for ACA naught. See, when you're in, if you have ACA naught, Dedekind cuts and Cauchy sequence, all that stuff, it's all equivalent. But when you're talking about RCA naught, you have to be much more careful. All right. You can see all that from Simpson's book. This system now pins down R and the partial functions from Q star into R star in the right way so that we now have a faithful extension of RCA naught, which does at least some beginning analysis, some basic real analysis. All right. Now let's go back to not having this, or even just this. Well, for venturing into such third order contexts, we actually should begin with this. This is simpler. This is just the subsets of R star. And there's already, I should probably say this here. And there's already quite a lot of real analysis you can do, even before functions, even before continuous function and stuff. You're looking at point sets, and there's limit points, boundaries, all this kind of stuff, right? So you have to approach this in little stages. All right, here to have a faithful extension of RCA naught, or even the top standard system, we need to pin down S of R star. We can't just talk about general S of R star. This involves restricting S of R star. The natural restriction in this context is on the intended interpretation, the Borel subsets. This is natural. I'm speaking semantically here. But this is too big a leap at this point in the development, in the SRM development. SRM is just much slower. Far too much SRM machinery is needed to take the plunge into arbitrary Borel subsets of R at this point. So we adopt the incremental approach, building up increasingly large families of subsets of R incrementally, treating increasingly large families of subsets of R incrementally, stopping to look at strictly mathematical statements that arise, their logical relations and reversals. So as you build this up, there's going to be some good old-fashioned RM-like work going on. A very important target is the semi-algebraic subsets of Rn. Expect all standard theorems in the semi-algebraic world to be provable in our present base theory. That's a good test. I can't swear to that. Getting into that is probably pretty time consuming, but still important. These are not just simply open sets, or I mean, these are complicated things, but it's well known that incredibly powerful things can be done with them that make them much simpler than you think, right? So the semi-algebraic subsets of the reals is just finite unions of intervals, right? That kind of thing. All right, so the idea now is to climb slowly and carefully up the low levels of the Borel hierarchy of subsets of the reals. It doesn't make any difference, finite sequences of reals, starting with countable sets and open sets. Investigate the status of all of the relevant mathematical theorems from descriptive set theory, establishing implications and also proofs that certain combinations are faithful extensions of the standard benchmarks from RM, limit points, closures, interiors, boundaries, exteriors, condensation points of closures. Condensation points being in the sense of closures, without introducing third order notions. So you should be able to get a lot of faithful extensions of standard formal systems we all use in RM. Then treat the nth level of the Borel hierarchy of subsets of R star for arbitrary n. I mean, along the way that, F sigmas, the F sigmas there's some elaborate material G deltas, things like, along the way. And they have their own reversals and reverse math type stuff in there. Most naturally, this is done using trees. So how you do this Borel hierarchy, use trees where the leaves are assigned open intervals in R. With rational endpoints given by those endpoints. All right, and omega splitting indicating union, and one splitting, or no, which is no splitting, indicating complement or variance thereof, right? You just get a recipe for the Borel set this way with the tree. Then we introduce real X lies at node U as a primitive with associated axioms. Not clear, that's probably the way. And then this avoids introducing any third order notions. You have to show that you've given all the good axioms that you want for that. Then you have to start proving theorems, see if you have enough power there to prove facts about the level of the Borel hierarchy, what happens, property of Baire and Lebesgue measurability and this and that, all this stuff. Then move to the full transfinite Borel hierarchy via well-founded trees and move cautiously into a third order by comparing. Now, cautiously into third order by comparing the transfinite Borel hierarchy with a characterization of Borel sets as the least sigma algebra containing the intervals. So what's going on there with the logic involved in the least sigma algebra definition coinciding with this transfinite definition? What's going on there logically? Let's see. Analyze that. And let me close by giving you another major challenge if this isn't enough for you. What about working out the strict reverse math of Kekris's famous DST book? There's going to be a lot of stuff probably early on that's like maybe pi 1 CA naught or ATR naught. It's not ACA naught is not going to handle Kekris's book, but ACA naught may handle a large amount of Royden's book. You see, that might be the case. So I think that that's all I really have to say about this wilderness. Thank you.